Alright, so for this video, I'm going to talk a little bit about what threads and mutext locks are. So, what is a thread? You can think of a thread as a unit of execution in a process, this being the same process. So, if I can sketch it out, let's suppose you have some process here. It can do whatever it likes. You can create multiple threads that kind of go do their own little thing that they're told to do. All coming from the same process, which means that there are a lot of things that they are sharing, and I'm going to get into this a little bit later. A way I like to think about it is you can maybe assume that you have a warehouse where you have a bunch of resources and things that you may need in order to run or work on something, and you just create a bunch of maybe little persons, whatever it is that you like, tell them what to do, and they kind of go off and do their own thing, coming all from the same warehouse. And maybe you have heard about the fact that you can have such things as multiple processes. You may be wondering, what is the difference between being multi-threaded and multiple processes? The answer is very plain and simple. Threads are much faster and lighter. And you may be wondering why this is the case. So in the previous example, I talked about how all threads basically come from the same process, which means that they don't need to have their own memory space because they are all using the same memory space of the process they came from. Versus multiple processes, you have a parent process, and then you can create a bunch of child processes, as many as you'd like. But the problem with this is that each child process has their own memory space, which in turn you can imagine why it would be a lot heavier to run something like this versus something like this. If you're coming from 225 to 233, you may already know what the heap and the stack is. Something that you can think about why multiple processes are heavier than multiple threads is because each process here has their own heap. And so instead of sharing one heap, every time you create a process, you have to allocate some heap to that specific process so that it can run whatever you're telling it to run. Now, how do you create a thread? There are two main functions that you use to create a thread, and this is pthread create. This is what you use to create, and then pthread join, which is basically what you use in order to ensure that the thread is done running. Now, in between this process, what pthread join does is wait for the threads to finish doing their work or terminate, and then in a way sort of joins them. Now, we can draw a line in here, which will signify every thread terminating. What terminates a thread? So a thread can be terminated by calling the function pthread exit, or maybe by returning from whatever function they were currently working on by exiting, or simply by signals like a user pressing Control-C. Once any of the threads, however many you created, it could be 1, 2, 3, 5, 100, however many you created, once one of these happens to a specific thread, pthread join will know that the thread has terminated, and they can now either move on to the next one or simply return. Here I have a little example of how you might want to create a thread. This is a very, very simple example of how threads might be used. You notice how I have this part over here where I'm going to call it a thread pool. And this is basically going to keep track of every thread I create so that later on it can be easier to track back when I try to wait for them to finish and join. So, like I said, you just use pthread create in order to create a thread. what you have to pass in is a thread address, which is what I'm currently doing here. The second argument is what's called the attributes of the thread. In this case, since I'm passing it null, pthread create will know to use the default attributes that it already has set for it. The next part is what I want my thread to work on. These are generally functions that you want to call, and you want to pass them in as a void pointer. And finally, this is whatever arguments the function that you are trying to call takes. So as you can see, down here I have my function print welcome message, which takes a size t variable, which is basically a number. And from what I'm passing from the pthread create function, it'll serve as sort of an index. So here you can expect to print anything from 0 to 4. Now, your instinct might tell you that the way this function is going to be called is in order, and you can expect to see the message as welcome to this mini threads lecture user, and then it'll print 0, 1, 2, 3, and 4. However, that's not the case. And the reason this happens is because once the threads are created, there is no guarantee of execution. This really depends on the priority that your CPU gives each thread in terms of how and when they run, which is why you can never expect or assume that whatever order you create your threads in is the order that they will be ran. So very well, as you can see, sometimes it'll run 0, 1, 2, 3, 4. Other times you may see printing out something like 0, 3, 4, 2. And that's just the behavior that threads have whenever you create more than one. Going back to this part, in the previous slide, I talked about pthread join. By creating an array of threads, what we called our thread pool, we, in this part, are ensuring that the threads end in order. So it'll start with thread at position 0. It'll wait for that one to exit in whichever of the 4 cases we've already discussed, and then move on to the next one. So while you cannot assure that they run in the same order, you can definitely assure that they end in the same order that you have created them. Now, in the first slide, I talked about how because threads come from the same process, there are a couple things that they share. And these 4 things that they share are the address space, the heap, any variables, and in this case, not just any variables, but variables that are global or on the heap. And I'll talk a little bit more about this later. And any file descriptors. And if you have not really dealt with file descriptors, all these are numbers that represent or point to a file so that C later on knows, scratch that. File descriptors are basically what allow you to open files through C, and they're basically just integers that represent a file. And actually, fun fact, stdin and stdout have their own file descriptors, and they also have their own sort of integers that represent them. Now, you may be wondering how it is that they share data. So if we go back to the first example where I sort of drew out your process and a bunch of threads coming out of it, or you can think about the warehouse example, where you have all your resources here. Because they are in the same address space and process, that allows threads to share the data with one another. So anything that is a global variable, anything that is on the heap, basically anything that is in the same address space as the process that they came from, they will all have access to. Because like I said, they are just instances of that process doing some work that they were told to do. So like I briefly mentioned in my warehouse example, where it might be a bit confusing, you can think that all of the resources that you may need, so basically your address, your heap variables, your heap in general, file descriptors, and more are all here. And when your threads leave this warehouse, they will leave with those resources on them, or with access to those resources. So, simply put, they are in the same address space and process, which basically means that they'll have access to anything that is in that address space and process. And that's how they are able to share the data and basically have access to the data of wherever they came from. Now, earlier I said that it was only heap variables and anything on the heap that they shared. They, however, do not have the same stack, and each thread has its own stack. And you may be wondering why. So I put a simple sort of analogy for this. You can think of the stack as scratch paper during a CVTF exam. And you can imagine that you and your friend who's taking a different exam in a different class go to the CVTF at the same time. And so you and your friend are the threads. You each have to use your own scratch paper because you need your own space. So you can freely write anything you need in order to successfully execute your exam. And once you're done, you basically just crumble it up and throw it away. And so that's what each thread does. They are free to have their own execution code. They sort of need their own space to do whatever it is they need to do in order to perform the task they were told to do. And so that's why they need to have their own stack, because if they were to share the stack, that means that they would not be able, they would not have control over the specific variables they need for that specific space or execution code they are trying to perform. Now, when it comes to multi-threaded programs, there is one very important thing called race conditions. And so, remember how I just told you that threads share certain variables? Imagine that you have the following scenario where you are trying to eat pizza and you create all your threads over here. And by the way, I just realized I forgot to put my little loop down here that joins all my threads. So I will write it down real quick. Okay, so now that I've added that, sorry about the messiness. You are creating all your threads here, which is calling the function eat pizza. And what this is passing in is basically a thread data element or instance of a structure, which simply I just put it for this case to hold a username and an index. And so if you can see right here, I am assuming that this method will be called with something like /pizza and then a bunch of different names following it. And what I do is I basically traverse this by going through argv and populate my thread data elements with the respective name and index. Okay, so now back to the example. Right here I'm saying that while I have slices of pizza, basically keep eating and print out a message saying like, hey, username, whatever your name is, you get some pizza. And now obviously once a user gets a slice of pizza, you want to decrement it from the global variable that we have right here, which is your pizza slices. Now, be the problem with this? The problem with this is, like I said, you don't know in which order your threads are going to execute whatever code you're telling them to execute. And not just that, but you also don't know whether they are running in parallel, concurrently, or one after the other. Generally, they will run in parallel or concurrent. That's why threads are used, so that you are able to execute multiple tasks at the same time. And so what happens if you have multiple threads trying to change this variable? You will run into an issue because you might decrement beyond 0, or you might want to make more pizza more than once, just because if, for example, you create, I don't know, let's say that instead of however many names I was passed in, let's say I was passed in 16 names, and all my threads suddenly call pizza slices, decrement, 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 and I get to 0, and let's say that one of those threads was already able to call make more pizza. This will be called more number of times that you want, because they are all trying to modify the same variable. So race conditions come around basically whenever you have shared data between threads that could potentially be accessed and read from at the same time. As you can see here, we can have a if statement that checks whether pizza slices are equal to 0. And the tricky part is that while one thread might be reading from this, like reading from pizza slices here, another thread might be modifying it at that exact same time, which means that technically pizza slices shouldn't be 0 anymore, but because you were not able to control the access to that data, it is happening at the same time, which could lead to undefined behavior. Now, the tricky part here is that race conditions do not break your code. I could very well compile this and try to run it, and I will get some behavior that I probably won't be able to explain. Sometimes I might actually to see the behavior that I expect, but it will not be consistent, and I will not see that the entire time. You can think of race conditions as warnings instead. And in order to do this, you have to run your code and compile it with what we call TSAN, which is a thread sanitizer. What this will do is whenever you run your code with this, it will tell you, hey, you have a race condition in such and such line, which basically means there is a possibility that two threads will be accessing the same resource at the same time when they really shouldn't be, and they should basically just be waiting for one another to either modify that value or finish reading from it. And so this introduces us to our next topic, which is the critical section problem. This basically talks about the shared resources to make sure that the above scenario we just described, where there are two threads accessing the same resource when they shouldn't, does not happen. And any critical section can be thought of as the section where we are accessing variables that threads share. So in this code, we can look where we are accessing variables. In this case, as we said, is the pizza slices variable. That is a global variable that all threads share and you're trying to modify. So if we identify that and basically identify where we are trying to modify it, we can identify our critical sections. So here, our critical section would be composed of this, because you're trying to both modify and read from a global variable, and here, because you are trying to modify, again, a global variable. And so you may be wondering, okay, but how do I solve this? I want to write a really fast and efficient multi-threaded program, but I want to make sure that this does not happen. And so this is where a mutex lock comes in play. Mutex locks basically basically come to the rescue of the critical section problem, and you can think of it as passing around a key. So what you do is you put a lock around your critical section. So in this case, we would probably try to lock around here and around here. Once you create your threads, they would all go to your critical section or start running the code in whatever order they need to run. And whichever one gets a hold of the key first is the one that will be able to run that critical section. Once the thread is done, it gives the key to the next lucky thread that is up in your priority queue about to run that critical section. And so, in order to use a mutex lock, there are four important functions that we use. pthread mutex init, as you can imagine, is basically just to initialize. And you can actually also use what we call a global initializer. And for that, you simply have to do something like you have your pthread mutex lock t is equal to pthread, typo, mutex initializer. Now, generally, this function is preferred simply because a global initializer only really works if your mutex is on the stack. So if you have any other types of variable like static or auto, this may not necessarily work, which is why it's almost always preferred to use pthread mutex init. Now, pthread mutex lock is what gives, in a way, the key to a thread. Unlock is what takes the key away and gives it to the next one. And once you are done, basically, you just have to destroy your mutex lock, and that means you're done using your pthread mutex or your mutex lock. So in this case, we would probably want to write something like, right here, we can just have pthread t, not pthread t. Some of these names are long. So pthread mutex lock m. You generally initialize it in sort of like your main process or where you're going to be creating all your threads. And so I would call here pthread mutex init. Pass in the address of my mutex lock. And why am I passing in the address? That's just simply because all these functions take a pointer to a mutex. This should be pthread mutex t. So once you initialize it, you can now put them around the critical sections. So I would, right here, put something like pthread mutex lock I'm writing a little bit of a shorthand because it's long. And then I would put another unlock here. Again, shorthand for whatever it is right here. This is shorthand. Now, you want to make sure that for every lock you have an unlock, and you want to think of every possible scenario. So we are locking right here, right? Oh, sorry, that should have been around the while loop, because you're accessing it here. So you should have no, scratch that. It was right where it was. So we're locking it here, but you have to think of the scenario where it doesn't ever go into the other if statement. So for that, all you have to do is basically add another unlock here to make sure that you're not infinitely locking a piece of a section of your code that will never be unlocked, and that could lead to deadlock, but that's for a different lecture. And so you would basically do the same over here. You would lock it and then unlock it once you're done. Now, this will ensure that even though you have multiple threads running at the same time, you are only able to read from global variables and modify them once at a time so that your numbers are accurate. That's basically all a mutex lock is, and that's why they're really, really helpful when you're running a multi-threaded program. Now, I previously mentioned that the point of creating threads is so that multiple instances of your process can be run either concurrently or in parallel. So you may be wondering whether it is possible to create more threads than CPU cores. So for example, if you have a 4-core CPU, is it possible to create 5, 6, 7, or 8 threads? And the answer is yes, it is possible. And it is actually sometimes better for performance. So the reason behind this is your threads will almost never need 100% of your CPU time, which means that your CPU will be able to allocate whatever time your threads need in order to run the specific task you've told them to run. Going back to your example of a 4-core CPU, what would happen if you have 5 or any more sort of bits of tasks that you have to run? It'll be a lot faster to create 5 threads so that each one of them can take a piece of the task, rather than creating 4, waiting for these to finish, and then these take over the next 1, 2, or 3 tasks that were left over from the first time. And so basically that is the reasoning behind creating more threads in CPU cores. It really depends on the number of tasks that you want to run, but it is possible, and it generally leads to better performance because it allows you to run more work along with any high latency tasks that you may already have running. And so finally, in order to end this short lecture, I'm gonna go over a very simple linked list or thread safe linked list. And for this, we're just going to assume that we have some sort of struct linked key that holds information about our node, which generally is something like the value they hold and the next node that they point to. And we are also going to assume that we already have some sort of main process somewhere else that is calling our linked list functions. So why is this thread safe? When you're writing code for data structures, for example, this can either be for a queue, this can be for a dictionary. You can make all those data structures safe. Generally, the version that C provides is not thread safe, which is why you might want to create your own instance and your own implementation of a data structure in order to ensure that it is thread safe and that you can use that linked list or use whatever data structure you're trying to use with multiple threads. And so what do you have to be careful of? Again, going back to the first example, look for shared data. So what are global variables? What are the resources that 2 threads might want to access at the same time? That same resource. So again, not stack variables, but resources that they share. In this case, you can see why we didn't put a mutex lock around this, because this is specific to the stack of this function, which means that no one else will be able to access this new node that you're creating. Only the thread that is currently running or the thread that is creating that node is the one that will be able to access it. Now, we will put a mutex lock around this part. And why is that? Well, we're modifying the head, and the head, as we can see, is a global variable up here. So we know that, for example, in this case, we're trying to push. For linked lists, what make them fast is that you have fast insertion at the front. So for this, we're just assuming that you're inserting at the front of your linked list. And so because you have to deal with modifying your current node's next pointer to the head and so on and so forth, that's why you have to add your mutex lock around this area so that you ensure that there are no two threads trying to move around the head at the same time, and this will lead to undefined behavior. Now you may be wondering, well, doesn't malloc put things on the heap? Yes, it does. Which is also why, even though, for example, as you can see here, this is not touching the head at all. This is just dealing with your new node. So this is because once you've called malloc, your program has already put it on the heap. It is no longer a stack variable. And that's why you also need a mutex lock around that. So that serves a nutshell of our push. Remove is very similar. Like I said, you are dealing with your head. So you just want to make sure that the axis is accurate and that any modifications that you're trying to do happen in the order that they should happen. There's no undefined behavior. So you lock this section over here. You're checking whether it's empty or not. And then you do all the fun stuff that if from 225 you probably wrote a much more complicated version of the linked list, or even in 126. Now, as you can see, I have two unlocks. And I talked about thinking about multiple scenarios earlier. So you want to make sure that if your code is never able to enter this if statement, so basically if your linked list is empty, you want to make sure that you unlock this area so the next thread can work on it. Otherwise, it will just be locked forever. No threads will be able to access it just because you've caused the deadlock. Basically because you never unlock that mutex, and so every thread that comes and tries to grab the key will think that someone else already has it, even though no one is even working on that section anymore. And so finally, a very similar thing around this, just have two instances of unlock to make sure that your mutex is correctly unlocked. Sorry for the redundance. But yeah, other than that, that was it.